my sound? There it is. Okay. Okay, so it is Tuesday the 23rd, and we're back on track. Here we go. We talked about Newton's law of heating and cooling the other day. We're not going to do that today. We're going to be talking about Euler's method. We're going to do it numerically. Yesterday we did it graphically. That was when Hal actually tried to fit a curve to the slope field, would actually draw a curve. Let's see how that's done. All right, we're going to figure out behind the scenes how you graph a solution curve on a slope field, okay? So that's what Euler N is about. Remember Euler G, we don't write that program anymore. That's built into the TI-89. So how do you do Euler's method? Euler's method is a way to estimate points on the solution curve, okay, using the slopes in the slope field, okay? So let's try one on for size. Here's an example, all right? Well, let me give you this sheet. Follow this sheet right here. And this is worksheet 11.3. Here you go. 2, 3, 4. Who's the hat man? What the heck are you doing with the hat on your brains? Yeah. Uh-huh. Right. Okay. All right, so take a look at number 1. It says, consider the differential equation x prime equals x plus y. The same one we started with yesterday, by the way. Whose slope field is given in 1117, but nobody asked. We don't need a slope field right now. On page 530, yesterday's sheet, you don't have to worry about that. We could generate it if we need it. Use Euler's method with a delta x of 0.1 to estimate y when x is 0.4 for the solution curves with initial conditions in part A and part B. All right, so this is what they give you. Okay? They give you the differential equation. This is number 1 on page 534 in the Harvard Calculus textbook. Let's see, so dy dx equals x plus y. This is just like yesterday, right? All right. Now, they give you that. They give you an initial condition, y of 0 equals 1. This is part A, okay, on the sheet, 1A. And they're asking you to find y of 0.4 given a delta x of 0.1. Now, if they don't give you the delta x, it's up to you. The smaller the delta x, the more accurate your answer is. The smaller the delta x, the more work you got to do. And that's why we're going to write a program. If delta x is really small, we'll let the calculator do it with the program, right? But first, let's see how this works so we can write the program. All right, so what I do usually is I make a little table. Yeah, a little table here. A column for x values. Whoops. Let's make that vertical. Column for y values. A column for delta y values. Delta x is given, or you choose it, but it's fixed. Delta y will change. Okay, so here's the x column, the y column, and the delta y column. Now, how do you get delta y? Well, see, they're giving you a delta x. So you're going to go through the slope field from your initial condition from the point 0, 1. You're going to sample the slope there. What's the slope there? If you plug in 0, 1, what do you get? What's the slope? Plug in 0, 1, you get the slope is 1, right? So what we'll do is we're going to say, okay, we're going to pretend that delta y over delta x is 0.1. I'm sorry, not 0.1. You said the slope was 1, right? So how do you get delta y if you know delta x is 0.1?
You multiply delta x.
You multiply, right? Okay, so this is what we're going to do. We're going to say, well, yeah, but it's not always 1. It's x plus y. So how do you get delta y alone? You multiply, right, same idea. So that's what I'm going to do here. I'm going to say, okay, this is x plus y times delta x. Now, what's the initial x and y? They usually give you initial conditions. What is it? 0 and 1. What's your first delta y? Plug in stuff. Plug in what? 0, 1, and 0.1. Okay, so 0 plus 1 times 0.1, that's 1 times 0.1 is 0.1, right? So what's your next x value? What's your next x value? 0.1, because delta x is 0.1 throughout. So to get the next x, you add 0.1, you add 0.1, you add 0.1 all the time. Delta y is going to be changing. What's your next y value now? 1.1, because it was 1, and delta y is also 0.1. That's a fluke. That delta y and delta x are equal. They don't have to be. All right, so let's do it again. What goes on here? Plug in for x what? 0.1. So 0.1 plus, plug in for y what? 1.1. So you got 1.2 basically, right? Times the delta x, which isn't changing. What's 1.2 times 0.1? 0.12. All right. I'm going to need some room over here, so this is going away. All right. So what's the next x? 0.2. Delta x is always 0.1 in this question, okay? So that's not going to change. Delta x is always 0.1. But now delta y is different. What is it? 0.12. So add it on to your previous y, you get an estimate for the next y. 1.22. Okay. So far, so good. Continue. When do you want to stop? Well, it says you're going to do this until you get an estimate for y of 0.4. So we want to do it once, twice more. Right? I want to know what y is when x is 0.4, right? So I'm going to do this 2 more times. Okay. So how do you show the work here? You plug in what? 0.2 plus 1.22 times 0.1 equals stop. Okay, what's this? Oh my goodness. Let's see, during a free period. All right, you've got mail. Spencer, Arthur, and Mariam. Oops, where'd you go? Oh well. Come and get it, Spencer and Arthur, during free period from your guidance peoples. All right. And YouTube really was interested in that. So what is that? Well, this is going to be what? 1.32 times 0.1 is 0.132. Is that correct? Wait, what did I do? Did I do something weird? 142. 142, yeah. 142. Okay, right, that's right. Okay, so we already know all the x's, right? Because we added 0.1, 0.1, 0.1, 0.1, right? That's the delta x is always 0.1. We don't know the delta y all the time. We've got to figure it out. So add this delta y to this y, get the next y. What's 1.22 plus 0.142? You get 1.362, don't you? Okay, so there's your estimate for this. All right, let's do it one more time to get y of 0.4. You didn't see that? Yeah. Okay, so we write 0.3 plus 1.362 times 0.1. This is going to be 1.662, right? So it's 0.1662. Is that right? Did I do that weird? Yeah, no, that's right. Okay. So we're going to take the previous y and add that on. 0.1662. And you get a 2. You get a 12 carry the 1. Wait, I'm looking at the wrong thing. Sorry. 2 and 0, right? So you get 2, you get 8, you get 12 carry the 1, and that's a 5, right? So 1.5282, and I don't need to do any work here because I'm done. That's an Euler's table. That's Euler's method, okay? It's a numerical estimate for values along the curve. What did I do what? Because I don't have to do any more work. I'm done. This is what they wanted. They wanted y when x is 0.4. So this is y of 0.4. I'm done. So I don't actually have to do anything here. Right? So if that's a differential equation, these are our estimates for points along the curve, the solution curve, that satisfies that differential equation and that initial condition. Okay? If you had a different differential equation, different initial condition, you get a different table. That's all. Okay, is this terrible? No, it is not. Okay, so we're basically trying to figure out points that Hal is plotting when Hal tries to plot a solution curve in diffie mode. That's what we're doing. And that's what Hal does, is if Hal has a default delta x set at 1/20,000th or something, some insane weird number. You could probably change it somewhere. I'm not sure where, but there you go. Okay, let's try that again. Try, let's see, what's this doing over here? Try number 2. All right, so here's number 2. On the sheet. Use 10 steps of Euler's method to determine an approximate solution for the differential equation y prime is x cubed with initial condition y of 0 is 0 using step size delta x is 0.1. Again, they don't have to give you the delta x. You can choose it. The smaller the better. Very often they do give it to you so they can, they know what the table is going to look like ahead of time. But all right, so what do we got? We've got dy dx is x cubed. Now, is this one that you really need Slofield's or Euler's method to to solve, or could you variable separate and integrate this? You could variable separate and integrate this and get an exact answer. And that's what Part B is about. Part B is compare your approximation from Part A to the correct exact answer in Part B, because you can do variable separable and compare. But remember, this is our fallback position. Solve fields in Euler's method is always our backup plan if we can't variable separate. Okay? All right, so what are we given? We're given y of 0 is 0. And we're given that delta x is 0.1. Okay, so let's make a little Euler table. Yay! Let's see. We're going to need a lot of space here. Well, I'll write small. On what? Oh, yeah, I know. Don't worry about it. You know what? I'm not going to stop it because I learned a lesson the hard way yesterday. The internet blew up, 9th period, so I couldn't record anything. So the only thing I could store for the FTP site was the 15 minutes I recorded here. So I set this up to 60 minutes. So if, for some reason, 9th period blows up, I can store this, whatever we do here, and I can crop this for YouTube too, both, all right? So just in case, because yesterday's recording on YouTube is 10 minutes as always, but on the FTP site was only 15 minutes, what we recorded first period. So I'm just going to record everything. Okay, there you go. Yeah, because my recorder's on the internet, so. So here we go. We got a column for what? X, a column for y, and a column for delta y. Now, how do you get delta y? Well, we pretend that this is delta y over delta x. How do you get delta y alone? This is delta y, this is delta x. Pretend. Just multiply by delta x. So delta y is x cubed times delta x. That's what it is. Okay? So, how do you start? X is 0. Y is 0. Delta y is 0 cubed times 0.1, right? Does anyone see what I'm doing? Which is 0. Okay, fine. So what's x now? 0.1, because remember, delta x is still 0.1. So all the x's are increasing by 0.1, 0.1, 0.1. Delta y is 0, though, so what's y? 0. Okay. I'm trying to write a little smaller so I can get 10 steps in here. I don't know if it's going to work out, but all right. So what do I substitute here? 0.1 cubed, right? Because 0.1 is the x value. I'm plugging into x. Delta x is 0.1. Well, what's 0.1 cubed? Well, what's 0.1 to the 4th, actually? 0.0001. Wow, that's a really small delta y already. So what's the next x? 0.2. What's the next y? 0.0001, because I'm just adding delta y to y. I'm just adding delta x to x. That's all I'm doing. It's very simple. Just add, multiply, right? Right? Okay, what's the next one? X is what? 0.2. We're going to cube it. And delta x is 0.1. Now, 0.2 cubed is what? 0.008 times 0.1 is 0.008. So what's your next x? 0.3. And what's your next y? 0.0009. Perfect, right? Is this terrible? The only problem here is I'm going to go 10 steps because I really want y of 1, I guess is what they're trying to get. It didn't say that, but that's basically what they're trying to figure out. All right, so here we go. What goes here? 0.3 cubed times 0.1. Well, 0.3 cubed is 0.027 times 0.1 is 0.0027. Is that okay? So this is 0.4, and this is what? 0.0036. Okay. And you know what? I'm going to cut to the chase. I'm just going to do one more. I don't want to do this all day. So let's say they wanted 5 steps, okay? So here's the 5th step. 0.4 cubed times 0.1 is, now what's 0.4 cubed? 0.064 times 0.1 is 0.0064, right? So this becomes 0.5, and let's see, what's 64 and 36? That's 100, so 0.01, basically. All right, so with an accuracy of 0.1, Delta x is 0.1, right? Remember, it gets more accurate as this gets smaller. Our estimate for the solution to this curve at y of 1/2 is 1/100th. How good is that estimate? This is part A, right? How good is that estimate? Well, part B is you can do it exactly and find out. Okay, let's do part B. 2B says, if dy dx is x cubed, how do you variable separate this? Simply say dy equals x cubed dx, which is what we did with the delta x anyway, right? And you can integrate both sides, can't you? So what do you get? Y is x to the third plus over 3 plus, no, what'd you say? Yeah, someone said x to the third. All right, x to the fourth over 4 plus a constant. How do you get the constant? Well, they gave you the initial condition, didn't they? So we plug in 0 for y and 0 for x, what's a got to be? 0. So y is x to the fourth over 4. Now remember our estimate for y of 0.5 is 0.01. How good is that estimate? Let's see. What's y of 0.5? Apparently it's 0.5 to the fourth over 4. Is that anywhere near 0.01? Well, 1/2 to the fourth is 2 4/8 16th. Divided by 4 is a 32nd, a 64th. That's a 64th. That's not quite 100th, but it's in there. Okay? So, let's see. Is our answer bigger or smaller than it should be? Is this an overestimate or an underestimate? This is bigger than 100th. This is an overestimate. When do you get an overestimate like this? So take a look at the slope field. All right, let's see. Take a look at what the slope field looks like. Let's go into y equals. Oh, I'm not. Okay, yeah, I got to get into mode and change it to diffq mode. And clear that out. Okay, and I'm going to clear that out. So what is it? It's just x cubed, right? So you should get what they call a quartic slope field. The curves through it look like quartics, sort of like stretched out parabolas. So let's graph. What'd I do? I did something stupid. Oh yeah, what did we say? It's not x, it's what? T, duh. You know, I know how to do this stuff, it's okay. Right? Yeah, there you go. So in, I don't know what zoom I'm in, I guess I think this is zoom 4. It sort of looks parabolic. Solution, you know, curves like y equals x to the fourth look like a parabola, but they're just sort of flat on the bottom. Okay, what if we ask it to do a solution curve through 0, 0, like we did? Didn't we do 0, 0? Yep. All right, so let's see what that looks like. Put in here, whoops, not here. Enter, 0, enter. And over here, put a 0. And see what the solution curve looks like. And what Hal is doing is Euler n, right? Euler, a numerical Euler's method, and then plotting the points that you get on the table. But it's doing a lot more points than we did. Delta x here is very small. All right, now I'm not sure. Can you trace this and see what points it came up with? Oh, it's still busy. All right, hang on. I need ludicrous speed. No. Okay. All right, so at t is 0, you get 0, right? Then, okay, my t step is 0.1, so I can get to 0.5 if I want to. And Hal's solution at 0.5 is 0.0155. Now, who's correct? Is Hal correct? Are we correct here? Or are we correct here? Which is it? Well, when the slope field is concave up, think about it. It's using a slope at 0 to estimate the point at 0.1. Then it's using the slope at 0.1 to estimate the slope at 0.2. It's off by a step. So when it's concave up, the slope I'm using is smaller than the one I should be using because I don't know it yet. So I'm underestimating. When it's concave up, I'm underestimating. When the slope field is concave up, I'm going to have an underestimate in Euler's method. When the slope field is concave down, I'm going to have an overestimate. Okay? So my answer is an underestimate. 0.01 is a hundredth is less than 1/64th. 1/64th is the exact answer. Is this anything like 1/64th? See, we got 0.01, but Hal says it's 0.015549. Is that close to 1/64th? I don't know. Let's see. What is 1/64th as a decimal? Pretty damn close. It was 0.155 something, but 1/64th is 0.156 something. Even Hal, with a delta x of 1/20,000th, is underestimating. Not by a lot, because the delta x that Hal uses is very small. Okay? Now, how do we control the delta x? If we want it to be really, really small, do you really want to write, say, a table where delta x, say the question was this, delta x is 0.01, and I want to get to x equals 1. How many times do you have to do this calculation? 100 times. Do you really want to do that? No, you don't. So let's write a program to do it, so we can control delta x even when it's small. All right, so let's write this very simple program. Okay. In fact, I'm just going to go straight to Hal here. All right, so let's go back to Hal, and let's go into program mode. Okay, so apps, program editor, and it's going to be new. And it's a program. Yeah, forgot about that. I should make a folder for this. Let's make all right, second escape is quit. Forget that for a minute. Let's make a folder. How do you do folders again? I forget. Mode. That's how you get to the folders, right? How do you make a new one? I think it's under varlink, isn't it? And then manage. So second minus, and then F1. And then create folder. Okay? There you go. And the folder I'm going to create is Euler. Okay, so let's see. Euler is, am I in alpha mode? Well, we'll find out. Yes, I am. E, U, L, where's my L? E, R. Yeah, usually, right? Okay. And there you go. All right, so we have a folder for Euler, and we got to get into it. So second escape this, I got to go to mode and change my current folder to Euler. And now I'm going to do apps, program editor, new. Program, yes. Euler, yes. And I'm going to call it, Euler N, Euler Numerical. Am I in alpha mode? Yes, I am. E, U, L, E, R, N for numerical method. Okay, let's write this program. It's very simple, actually. Now think about it. What do we have for input? We need the initial conditions, x and y, right? We need also the delta x, which remember when we did LRTE and MTSC, right? The Riemann programs, we called that H. It was the height of a trapezoid or something when we did traps. So I'm going to call it H again. And then I'm going to say how many times do I want to do this? All right, so I'm going to tell it how many times to do it. Like in this case, I did it 5 times, right? So that's my input. So let's input stuff. Okay, so it's going to be F3 for I/O. Prompt is choice 5. I'm going to prompt for X, comma Y, comma alpha H, which is the delta X, comma alpha N, which is how many times you want to calculate stuff. Okay? So enter that. All right, now I need a loop. I need to do this n times. So let's do a loop. F2, 4. All right, for what? For, let's see, some dummy counting variable, alpha I. You remember when we wrote programs? It was a while ago. Alpha I starts at 1, goes to n plus 1. You'll see why in a minute. Alpha n plus 1. And counts by a step of 1. All right, so the rest of the program is in this for loop. This for loop just goes n times, okay? What does it do n times? Well, let's see. This is what I'm going to do. I'm going to clear the screen. Where's clear I/O? I forget where the hell that is. I think I'm going to look in catalog. Do you know where clear I/O is? Yeah.
Why would
It's going n times. It counts from 1 to n plus 1, counting by ones. In other words, if I is 1, then add 1. I is 2, then add 1. I is 3, then add 1. I is 4, until you get to n plus 1 to stop. Okay? So that just says how fast to get there. That's called your step. All right. Clear I/O, I forget where it is. So let me go to catalog. And how about alpha C to get to the C's or not? I was in alpha mode, I guess. There you go. And clear I/O is here. You'll see why in a second why I'm doing that. Now, you may have a lot of values to do here. So what I'm going to do is I'm going to print out all the x's and y's as they occur. Okay? So let's do that. I/O, display, x, enter. I/O, display, y, enter. So it's going to print out every single x and y it comes up with. It's going to pause so you can write it down. So like if there's 100 of these, it'll just zip through 100 of them. You won't see anything, right? So I need a pause. I forget where pause is. How about catalog? Hit P and find pause. So it stops after it prints each x and y. Waits for you to hit enter, and it'll calculate the next x and y. Now, here's the crux of the matter. How do you calculate x and y? All right? The next y is the old y plus delta x, which is alpha h, times the derivative there, which I'm going to put in y1. So y1 of x. Okay? That's going to be stored as a new y. All righty? And how do you get the next x? Well, that's easy. X plus delta x, which we called alpha h, is the new x. That's the whole program. Yeah?
Y plus H in parentheses.
Y plus, where are you? Y plus h? No, because it's h times y1 that I want. This is like x plus 1, this is like x cubed times delta x added to the old y. Right? So that's added to that. So I'm just automating what we did, yeah. Store, STO, near the on key on the bottom left. STO. All right, let's test this out. Let's run it for this table, see if we get the same results. That'll be a test to see if this program works. And then we can use it to generate really, really small delta x's. Everyone got that? Should I make it a little bigger, maybe? Zzz. Yeah, it's hard to do that when I'm typing, but now that I'm done typing. All right, that's basically the whole program, isn't it? Pretty much. Except for the clear I/O before the prompt. But, well, I guess I don't really need that. I skipped that anyway. That's everything we wrote, right? That's everything. All right, so it fits on the screen. Great. All right, so you almost got it? Okay, let's test this out then. So how do you run this? Well, precondition is that you put the differential equation that they give you into y1. So second escape for quit, go into y equals, and well, now I got to be in function mode. So mode, function mode. All right, so I'm going to put x cubed here, whatever the differential, whatever dy dx equals, I'm going to put here. Okay, so x, enter x cubed. Okay, and quit that. Now let's run the program. Second var link, go to Euler n, enter, close the parentheses, enter. All right, so what's your first x? I'm trying to do the same problem. 0, then 0, then 0.1, then how many times did we do it? 5. All right, so the first output is 0, 0. It's waiting for you to write it down on your test paper. Hit enter for the next one. That's a pause. 0.1 and 0. Enter. 0.2 and 0001. Enter. I'm in fix 6 for some reason, whatever. 0.3 and 0009. 0.4 and 0036. 0.5 and 01. Perfect. This program is working perfectly. In fact, it checked our work over here. So we did this right, too. All right, now the question then remains, if you hit enter, it'll stop, right? Have F5 to exit the program screen. The question remains, though, how do you enter a question like this, where there's x's and y's? Does that work? Let's try the program on this. what would you do first to do this table on the program? First thing I got to change is what? y1. Make sure you're in function mode. Go to y1, and we're going to type x plus y. The way we wrote the program, it's going to use this y as necessary. Okay, so enter x plus y. There isn't an alpha y, right? I didn't use alpha y in the program anyway. All right, good. Okay, there you go. All right, quit that and run the program. Hit enter. It's sitting right there, so you can just hit enter to run it. And see, I should have had a clear I/O on the first line because that's junk, but whatever. All right, so you tell me, what do I enter? 0, 1, and how many times did I do it? Well, sorry, delta x is what? 0.1, and how many times did I do it? This table? 4 times, okay. So 0.1, we knew that. 0.1 and 1.1, good. 0.2 and 1.22, good. 0.3 and 1.362, good. 0.4 and 15282, good. All right, now, what if we want to make this really accurate? Can we run the same program, but instead of 4 times, let's make it 40 times? In other words, I'm going to make this 0.01 and get to 0.4 by 40 iterations. Can I get a better estimate? That's the idea. Okay, let's try it. All right, run it again. It's the same. I already put this in y1. It's the same. This is the same. Initial condition is still 0, and it's still 1. Now I'm going to do a delta x of 0.01, and I'm going to go 40 times. And, well, that's sort of silly, but let's click, 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 click. I just want to know what happens when I get to 0.4. See how my answer changes. I'm just hitting enter, 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 boom. So look, my answer now was 1.5282. My answer now is 1.5777-ish, let's say. So it's increasing. As delta x goes to 0, this approaches the correct answer. Apparently it was an underestimate. It's approaching from below. It's getting bigger and bigger and bigger, getting closer to the right answer. Now, you could play with this a little bit. Hit enter to the end. Hit F5 to get out. You could go to apps, 7, current, and kill this pause line when you don't want it. Say you only want the last result. And leave it blank, because you can put it back in if you want. Now run it again. 0, 1. Well, let's make it crazy. 0.001. Let's go 400 times and see what happens. Maybe I should use ludicrous speed here. And the answer is going to be bigger still than 1.577 because it was an underestimate. It's getting bigger and closer to the right answer. But now we have to do 400 iterations, and maybe I should do ludicrous speed. Can I do ludicrous speed here? There you go. And now the answer is bigger still. 1.583 something. Now I have no way to check what the exact how good that is based on an exact answer because I can't do this by variable separable. This is the best answer you're going to get. This kind of an answer, depending on how many iterations you do it. For 10 iterations, we got 1.52. Whoops, ludicrous speed is too ludicrous. Wait, hang on. Turn that off. It goes to sleep mode too fast. All right, for 10 iterations, no, wait, what was it? 4 iterations, we got 1.52. 40 iterations, we got 1.57 something. 400 iterations, we got 0.58 something. We're getting closer and closer to an answer. There's a limit here. Okay? All right, try it again. 0, 1, 0.0001, 4,000. No, whoops, whoops, whoops. I didn't hit enter apparently. Yeah, I really want ludicrous speed. Yeah, don't do this at home. You don't have ludicrous speed on your calculator, right? All right, so we got 1.52, 1.57, 1.58. Let's see what we get now. I should have probably written this down as a convergence table somewhere. Fix 4 probably would have been nice, but we're getting there. We're halfway there, more than halfway there. We're 3/4 of the way there, going up to 0.4 hopefully. And there it is. 1.58 something. So it's almost the same answer. I think it was 1.582 something, Now it's 1.583 something. So you're basically going to get 1.583 probably out of this. What if we try the same thing on this problem? Because this one we know the answer. The answer was 1/64th, right? And remember what 1/64th is. (1/64th) as a decimal is 0.15625. That's an exact answer, right? That's an exact decimal. Can we get a better answer than what we got? Let's do it. Go to y equals, change this to x cubed. Second quit, and let's run the program. All right, so now it's 0, 0. Give me a 0. And before it was 0.1 in 5 iterations. How about we do 0.01 in 50? Don't forget to put the pause line in there if you're trying to copy down the results as a table. And let's see what we get at 0.5. A little bit closer to the right answer. Remember, we know the exact answer. 0.1, what the heck was it? 0.15625, right? 0.150 now. Okay, fine. Run it again. How good can you get? 0, 0, 0.001, and 500. And do I need a ludicrous speed? I guess so. Oh, 15563. Okay. That's closer. 0.15625 is what we're trying to get, right? So we can get really, really close to the right answer, even if we don't know the exact answer. In this case, 20/20 hindsight, we know the right answer. Anyway, that's the idea. So any questions on how to do Euler's method by hand without a calculator? And how to use the program if you need it? Okay? That's basically it. Any questions? All right, good. We're done. Let's save this up. This is unit 11, 812, right? Okay, so let's stop this.